I hope you have a good understanding now of how to compute the truth value for a sentence of our system when you're giving the assignments to the simple sentences. Now it's time to start exploring logical relationships within our system, and we use those as a model for logical relationships as they occur between actual statements. And in order to do that, we need to look at a truth table for a sentence. To do a truth table for a sentence, instead of computing the value of the sentence on just one assignment, we look at every possible assignment and we see what happens with our sentence on the various possibilities. So let's take the example of a sentence like A dot tilde B, that is A and not B. In order to compute the truth value for this sentence, we have to know the values of the simple sentences because those are just assigned. The simple sentences that are involved are A and B. So now the values of our complete sentence will be determined by the values of A and B plus the rules for the operators. And we want to look at every possible assignment of values to A and B. We've done this sort of thing before, and when we have two simples involved, these are the possibilities. They could both be true, the first one true and the second one false, the first one false and the second one true, or both false. So now all we need to do is compute the truth value of our complete sentence for every value of the simple sentences. I did mention when I was giving you an overview of this system that it's more efficient to go column-wise and determine all the values for each sub-sentence before going on to the next larger sub-sentence. So this is particularly true if we start by rewriting the values for A and B, and now I still proceed according to my order of operations, except that I compute the value for every assignment. So the first thing I need to do is the tilde. My order of operations is parentheses tilde, and so I have a tilde inside the same parentheses with the dot. Tilde comes first. So I'll just go down the column, and tilde B, not B, is assigned the opposite of whatever B is on each assignment. So that's false, true, false, true. And I have suggested that we cross off the values for B. Now that we're done with B, we can cross off all the values for B. And I'm using a highlighter. Remember, highlighter means ignore. Now I can compute the values for the dot statement. And the right side of my dot statement is the value that I just got for tilde B, or not B. Meanwhile, the left side is the values for A. And I just go down the column and determine the value according to the dot rule on each row of my table. The rule for dot is that it's only true when both sides are true, so that only happens here on the second assignment, and on the rest it's false. Now I'm going to cross off the values that I used to get the dot. And it's going to be important later on when you're trying to discover logical relationships that you know which operator is the main operator of those you're dealing with. And in this case, it's the dot. We've talked about how to find the main operator, and if you complete these truth tables the way I'm suggesting with the order of operations, then automatically the last one you did will be the main operator if you've done everything correctly. So you have two ways of determining the main operator, and they should agree. If they don't, you've done something wrong. What we end up with here is sort of like a logical profile of this sentence, A and not B. We have a list of potential values for A and B, and what A and not B ends up being for each case. And it turns out that there's nothing particularly surprising or special about this sentence A and not B. On some assignments it ends up being true, whereas on other assignments it ends up being false. So this is what we call a contingent sentence. A contingent sentence in our system is one that's true on some assignments and false on other assignments. Some sentences end up being sort of logically weird in ways. You can have a sentence that ends up being true on every single assignment, and that's what we call a tautology. So take a look at this example. We have either A only if B, or either not B or A. Symbolically, A arrow B, in parentheses, wedge, and then in parentheses, tilde A, wedge A, tilde B, wedge A. This is another sentence that's built out of two simple sentences, A and B. So we can start by listing the possible assignments for A and B. Again, both true, first one true and second one false, false and then true, or both false. And I want to compute the value of the entire sentence for each assignment to the simple sentences. I'm going to start by repeating the values for A and B underneath the A and B in my sentence. Now I'm going to go through and compute the parts of my sentence following the same order of operations again and the rules for each operator. I have two sets of parentheses, and I need to compute those values before I can compute the value for the main operator. It doesn't really matter which set of parentheses I complete first, just like with arithmetic, as long as I do both these parentheses before doing the operator between them. So let's start with A arrow B, which can be A only if B, or A implies B. Although there are some issues with the latter, it's a convenient way to pronounce the arrow. And the rule for the arrow or horseshoe is that it's only false when it's true on the left and false on the right. So that happens here on the second assignment. And on the rest of the assignments, it's true. And now I'm going to cross off the values for A and for B. Meanwhile, over on the right side of the wedge, I have another set of parentheses. And so I have to compute the values in there. And inside this parenthetical group, there are two operators, a wedge and a tilde. So our order of operations means we start with the tilde, and we do the value of tilde b here first. So we go down the line, and it's the opposite of whatever b is. So false, true, false, true. And now I'm going to cross off the values for b. Remember that highlighting here means ignore. So when we do the wedge statement, not b or a, we need to make sure we're using these values from the left side, the values we just got for not b. Those are what feed into the wedge rule, not the values under b. You'll get the wrong answer if you do that. So the rule for wedge is that it's true as long as at least one side is true. And in the first assignment, the right side is true, so it's true. In the second assignment, they're both true. Now that means at least one is true, so it's going to be true again there. On the third assignment, both sides are false. So that means it's false on that assignment. And the last assignment, the left side's true, so that makes it true. When I proceed to the main operator, I need to make sure that I'm using the left side should be the result from inside the parentheses on the left, and the right side should be the result from the parentheses on the right. And that result is not the tilde. We use that to get the values for the wedge. So let's cross off that tilde. Now we also cross off the values for a. So now I'm ready to do my main operator, the wedge, using what I have left on the left side that's not crossed off, and what I have left on the right side that's not crossed off. And the rule for wedge, true as long as at least one is true. So on the first assignment, both sides are true, so that makes it true. On the second assignment, the right side is true, and that makes it true. On the third assignment, the left side is true, which makes it true. And on the fourth assignment, both sides are true. Now look what happens to the overall value for our complete sentence on all the assignments. It turns out true on every single assignment. So that's what we call a tautology, a sentence that's guaranteed to be true by its logical construction alone. Now we can have actual statements in English that are tautologies as well, but it can be a little bit tricky to detect them unless they're super simple tautologies. So if you have a statement like this one, either Al is home or Al is not home, you can probably tell that this is a tautology without looking at a truth table. Nevertheless, we can look at a truth table for the symbolic version, A wedge tilde A. And there's only one simple sentence involved. It's A, which is either true or false. And so tilde A or not A is the opposite. And when A is true, the left side is true. And when A is not true, the right side is true. And so, of course, this sentence is a tautology, just as you would have expected. But our formal language allows us to expand this concept. You might not have guessed that the previous sentence would turn out to be a tautology if you have a statement like either if Al's there, Bob's there, or else either Bob's not there or Al is there. It's not immediately obvious that that's a tautology. It's not immediately obvious what the heck that is. But now we're able to process that kind of statement in a systematic way. The other kind of logically weird statement that we can encounter is a self-contradictory statement. And a self-contradictory statement is one that is false on every assignment. Suppose we're looking at a statement like Al is home and Al is not home. This is another one where you probably don't need a system to be able to tell that there's something messed up about this statement. Al is home and he's not home. I mean, if that's a sufficiently specified statement, then both those things can't be true. And take a look at how this works out within our system. Our model for this kind of statement will be the sentence A dot tilde A. The possible assignments for A are true or false. If A is true, then tilde A is false. And meanwhile, if A is false, then tilde A is true. The rule for the dot is that it's only true when both sides of it are true. And in this case, that never happens. So this is an example of a self-contradictory statement, something you didn't really need our system in order to determine. But once again, we can greatly extend our ability to detect self-contradictory statements with this system. Even if you had some long, complex statement, if you get it into the symbolic form, then you can tell that it's a self-contradictory statement. Now, one thing you may have noticed in the process of doing these tables is that sometimes I do a table with only 2 rows like this one, whereas other times I do a table with 4 rows like this one. So what's that about? Well, remember the objective of setting up the table is to cover every possible assignment and then to track what happens to the complete sentence in each case. So the number of rows that we need to include on our table corresponds to the number of possible different assignments to the simple sentences that are involved in the sentence. So this sentence involves 2 simple sentences, A and B, and there are 4 assignments possible for those 2 sentences, whereas the other sentence, A and not A, only involve one simple sentence, A, to which only 2 possible assignments exist. So the number of possible assignments, and hence the number of rows I need on my table, depends on the number of simple sentences involved in the sentence I'm dealing with. And now is as good a time as any to show you the systematic way of setting up the possible assignments. So the first thing you need to know if you want to set up the truth table for a sentence is the number of simple sentences involved. So remember, in our symbolic system, each letter is a simple sentence. So the number of simple sentences is just the number of letters involved. So if I have A dot tilde B arrow tilde A, then the number of simple sentences involved there is 2. There's an A and a B. It doesn't matter that the A occurs twice. It only matters how many letters are involved, how many different letters are involved. And meanwhile, if we have a sentence like this one, A wedge B in parentheses double arrow C, then there are 3 simple sentences involved. Now, the number of possible assignments that you need to deal with is always determined by the number of simple sentences in the following way. You take 2 to the power of the number of simple sentences involved. Now, we could go into the reason why that's the formula. It involves the fact that there are 2 possible semantic values for each simple sentence, and so the number of possible assignments doubles each time you add another simple sentence. But let's leave that maybe for another time. If you really want me to explain that, I can. But I don't want to get on too much of a tangent, so let's just say that this is the formula. The number of possible assignments that you need to deal with is 2 to the power of the number of simple sentences involved. So if we have a statement with only 1 simple sentence involved, then the number of possible assignments is 2 to the first power, which is 2. And if we have a sentence with 2 simple sentences involved, then the number of possible assignments is 2 to the second power, which is, that's right, 4. If you have a sentence involving 3 simple sentences, then the number of possible assignments is 2 to the third power, which is 8. If there are 4 simple sentences, then you have 16 possible assignments. 5, you have 32, and 6, you have 64, then 128, then 512, and then 1024, and so on and so forth. Notice how the number of assignments possible goes up by the same pattern as RAM sticks and other computer-associated products. You know, first you would get 256 meg RAM sticks, then you would get 512 meg RAM sticks, and then you get 1 gigabyte, which is 1024, and then they go up from there. And that's because our system is a binary system by virtue of having 2 semantic values, and computers similarly operate on a binary system. They have a binary language as their machine language. And there are, of course, lots of other connections between logic and computers, but we won't go off on a tangent about that. Right now, we just have to learn about the logic. So now, once you have your number of possible assignments, you still need to make sure that you list every possible assignment to the simple sentences that are involved. That's quite easy if you're just dealing with 1 simple sentence, because you know that there are just 2 assignments, true and a false. But if you have to deal with more than 2 possible assignments, because you have more than 1 simple sentence, then it becomes helpful to have a systematic way of listing all the possible assignments. And it's especially helpful if you're dealing with 3 and 4 or 5 simple sentences. So suppose we're dealing with 2 simple sentences, and we got an A and a B. Then we know we have 2 to the second power, or 4 possible assignments. And we can systematically make sure that we list them all in the following way. Now, the procedure I follow is not exactly the same as the procedure in the book, but it is equivalent. You get the same result every time, and I find it to be simpler to describe. So let's start on the right with B. And we know there are going to be 4 possible assignments. So what we can do is we can start with B, and let's alternate trues and falses until we get to the 4th assignment. So true, false, true, false. Now go over to the other letter, and we'll alternate by twice as many. So we'll alternate by 2s. We'll do 2 trues and 2 falses. And if we follow that procedure, we know we have covered every possible assignment for our 2 simples. We have the assignment where both are true. First one true, second one false. First one false and second one true, both false. Now, if we're dealing with 3 simple statements, so we have an A, a B, and a C, then how many possible assignments do we have to deal with? 2 to the third, which is 2 times 2 times 2, which is 8. And in order to cover all of our possible assignments, we can use the same procedure. Let's start with the one on the right. Let's start with the C and alternate. So we'll do true, false, true, false, true, false, true, false. And then when we come to the B, we will again alternate by twice as many. So let's alternate by 2s. We get true, true, false, false, and then true, true, false, false again. Now, when we come to the A, we're going to alternate by twice as many as the last one. So we'll alternate by 4s, 4 trues and 4 falses. Now, this ensures that we have covered all the possible combinations of truth values assignments for A, B, and C. We have true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, and false, false, false. Try thinking of all those without having a systematic way of doing it, like we did with only 2. Not quite as easy. And if we're dealing with 4 simple sentences, an A, a B, a C, and a D, then we need to cover 16 possible assignments on a 16-row table. We could alternate on the D, alternate by 2s on the C, alternate by 4s on the B, and when we come to the A, we would alternate by 8s. And 16-line truth tables sure are a lot of fun, aren't they? Now, let's take an example of a sentence involving 3 simples, and let's see if it's a contingent statement, a tautology, or a self-contradictory statement. So let's try this statement. And by the way, it's a good thing to start reading these things off in terms of the half meanings that they have. So instead of thinking of this as A, double arrow, and then parentheses, and so on, I look at this and I see A if and only if either B or C or A. Now, there are 3 simple statements involved in our statement, A, B, and C. So that means we have 8 possible assignments. In order to cover all the possibilities, we can start with C and alternate true, false, true, false, true, false, true, false. And then when we get to B, we can alternate by 2s. So 2 trues, 2 falses, and another 2 trues, and another 2 falses. And finally, when we get to A, we can go 4 trues and 4 falses. The next thing we want to do in dealing with a sentence like this is repeat the values of A, B, and C underneath where they appear in the sentence. So I repeat the values for A, and then repeat the values for B, and then finally repeat the values for C. Now, one of the things I like to do when first starting out is you notice that I've listed the simple sentences, or the capital letters, off to the left, and then written out the assignments there before beginning with the sentence. However, since you end up writing the values of the letters underneath where they appear in the sentence anyway, as long as you make sure that you can keep your assignments consistent, you could just dispense with that step altogether and just start by listing the values underneath the letters where they appear in the sentence. So we end up starting with our assignments set up looking like this. And now we just proceed according to the rules of the operators and order of operations. We proceed to the smallest set of parentheses, and that's the B or C statement. And the rule there is that it's true as long as at least one is true. So the only time it's false is here on the 4th assignment. Oh, and on the 8th assignment. For the rest of these values, at least one side is true, and so that makes the statement true. Now I'm going to cross out the values under B and C because we don't want to be looking there again. So now we proceed outward to the larger set of parentheses, and the left side is what we just got, the right side is what we have for A, and it's wedge or again. So the rule is it's true as long as at least one side is true. So all of these are true except for the very last assignment where both sides are false. And now I cross off the values that I just used to get that under A and under the wedge. And that means I have my value for the right side of the double arrow, which is written under the wedge. It's the value for this entire parenthetical expression on the right side of the double arrow. And meanwhile, the left side of the double arrow is the values for A. And this is going to be my main operator. It's the last thing I'm doing, and it's also the main operator by the criteria that we set out before for the main operator. The rule for double arrow or triple bar is it's true when the sides are the same, it's false when they're different. So the first 4 values, it's the same. Then the next 3, it's different. And on the last one, they're both false, so that's the same again. So the result is that our sentence is contingent. Our sentence is true on some assignments, but it ends up being false on other assignments. And intuitively, the idea of a contingent statement is a statement which is not guaranteed by its logical construction to be true, nor is it guaranteed to be false. And whether it's a true statement or a false statement depends. It depends in our system on the simple sentences that it's made up of. And when we're talking about actual statements, the truth value of a contingent statement depends on what actual facts are true. Whereas when you have a tautology, it doesn't matter what the facts are. A statement like Al is home or Al is not home is going to be true no matter what. So we've taken this sort of common sense logical concept and we've extended it. For example, with a statement like A if and only if either B or C or else A, it wasn't obvious from the beginning intuitively that that was going to be a contingent statement, but it turns out that it is. So again, just to sum up what we've got here, every sentence of our system, and indeed every actual statement, falls into one of 3 categories. It's either contingent, which means it's true on some assignments, or false on others. In the case of actual statements, it's something that could be true or might not be true. Or it's a tautology, a sentence which is true on every possible assignment, or in other words, a statement that's guaranteed by its logical construction to be true. Or it's going to be self-contradictory, that is, a sentence that's false on every possible assignment, or a statement guaranteed by its logical construction to be false. So in this video, we looked at the logical status of a single statement or sentence of our system. Next, we're going to turn to looking at the logical relationship between pairs of statements.